today about convolutional Monte Carlo tree search rollouts applied to computer Go. All right, so one of the, I guess you can say there are two kind of really interesting things that have happened with computer Go in the past decade. So MCTS, that's one that people have heard about. So around 2006, the UCT algorithm came about, and that pretty much revolutionized computer Go playing. And more recently, in the past few years, deep learning has also become a really important and strong approach in general for lots of machine learning problems. For Go in particular, the combination of Monte Carlo tree search and deep convolutional neural networks have led to some pretty strong programs. So a sort of stereotypical view of how you can design today in the year 2016, what a strong computer Go program would look like is you take the tree policy, you put a deep convolutional neural network in it somehow, and then you put a pattern lookup policy in the rollout. In the rollout section, and this combination actually works really well. So, AlphaGo, I'm sure you've heard of it. That's basically what it does. It has several deep convolutional networks, and essentially they guide how the tree search happens. And in the rollouts of Monte Carlo tree search, they're still just doing the same patterns that people have been doing for the past decade, and this works really well. So the question is, what if we replace the pattern-based policies with deep convolutional neural networks too? So that's what the rest of these slides are going to be about. All right, so just a really quick recap of what I'm talking about when I say pattern policies. So let's say we're looking at this local section in Go, a local region of the board. This is what's happening right now. It's black just placed stone with a little red outline, and now it's white's turn to move. So what a pattern policy would do is it would actually look at some local regions and try to figure out what are the relative weights of placing a stone in those points. So let's consider two possible candidate positions above and below this, above and below black's just placed point. So we look at the top one. We take a 3x3 local pattern, we look up in some table that we have, and we receive the weight of one. On the other hand, we compare the bottom pattern, and I've just made up these numbers, but this one has a much larger weight of 99, so we want to play this bottom one instead. And of course, in addition to this actual pattern lookup, there might be some extra decision tree logic. Maybe we only play next to the stone that was just placed, and we ignore the other positions, for example. So a generalization of this is to look at, to apply a neural net and simply feed in the entire board position. And the output of this convolutional neural network is essentially a probability distribution over all the possible points. And we can essentially define a stochastic policy where we play a stone at a particular point with a probability determined by the output of this neural network. So in this case, we just feed in this whole board, and we end up with roughly these three, maybe four positions that have higher probability than the rest. So moving from pattern lookup policies to these convolutional policies, what are the advantages? Well, you can think of convolutional networks as a generalization or an extension of these pattern lookup policies. Because of this huge, there's been so much advances in deep learning in the past just 4 years. So we figured out how to get some really fast convolutions. You've heard of cuDNN. This is a fast software library for NVIDIA GPUs. We can take advantage of really powerful hardware. You can get 5 to 10 teraflop per second on modern GPUs. Teraflops, that's 10 to the 12 floating point operations. Really, really big. And also, there's also this burgeoning field of deep reinforcement learning. So essentially, we're taking the classical reinforcement learning approaches, but then we're applying deep neural networks to those problems, and that turns out to also work really well. And if we have convolutional networks in the loop, we can apply a lot of deep RL experiments to MCTS agents. All right, so if we actually want to apply convolutional networks for MCTS rollouts, so there are a few practical difficulties, or at least some criteria that we have to achieve. So first, we need to make sure that we're actually achieving some pretty fast rollouts. We want to maximize the throughput in particular, the number of rollouts per second. So parallelizing rollouts, the difficult part there is that they are naturally sequential. You are evaluating one game position, you get the next game position, you have to do this sequentially, essentially. And finally, if you want to get the best throughput on GPUs in particular, you need to somehow batch your convolutional operations, simply because this is the best way to utilize all of the cores on your GPUs. So this motivates this approach of batching the rollouts on in your MCTS algorithm. So then the question is, how do you go from sequential MCTS to batched MCTS? All right, so here's a pseudocode for what sequential MCTS look like. You have your selection phase. You take your tree search. You try to come up with a traversal through your tree, and possibly expand the tree nodes, and then you perform a rollout using your rollout policy, and then you back up the tree. So this is the classical MCTS paradigm. All right, so maybe just drawing this out to make it slightly more clear. So you have a tree. In this case, I'm highlighting a particular traversal in orange, performing a rollout. In the next iteration of my tree search, I pick a slightly different traversal, and I can do another rollout, and so on and so forth. So the batch version of this is, actually just before I go to the batch version, just if we zoom in on what the rollouts are actually doing. So the rollouts kind of are beginning at the end of the tree search section. So starting from an initial state in a rollout, we feed this state into whatever rollout policy, whether it's a pattern lookup or a convolutional network or anything else. The output of this policy is an action, and then of course we apply the action on the current state, and we get the next state. And then we do this iteratively until we end up with a terminal state, at which point we perform the backup in MCTS. Okay, so going from the sequential to the batch version of MCTS. All right, what does this look like? Essentially, essentially it's kind of like a loop. It's like inserting an extra loop in here. So we are performing, we preserve the actual tree within here. So all of these operations are actually operating on the exact same tree. Actually, there's a small typo here. I think the backup should actually be in its own loop. I think here, this is actually the slide that I care about. Okay, so all right, we perform a bunch of tree selections and traversals. Then we perform a single rollout in batch across all of the traversals that we've just created. And then we force back up the tree in batch as well. So essentially, during the rollout, we're actually seeing a single view of the tree and the parameters. So we can do this all in parallel. And remember, we can't actually really parallelize within a rollout. We have to parallelize across rollouts. That's why we're calling this a batch rollout. And if we actually focus in on what the rollouts are doing, well, this is all essentially, this is like one tree, one set of parameters. We're doing the rollouts all at once, and the backup is also happening all at once. And then zooming in on the rollouts again. So what does this batch rollout actually look like? Well, in this case, in this example, we have a batch size of 3. So we take this batch of 3 game states. We're sending this to our rollout policy, and in batch it's coming up with 3 actions. We apply those simultaneously to those 3 states, and then so on and so forth. And this operation you can do pretty efficiently on something like a GPU, especially if your rollout policies are convolutional neural networks. So this is essentially what the batching looks like. All right. One other thing is, because we're actually operating in batch, there's at least one other modification we can do. So normally in MCTS, you have a tree policy that's a combination of some sort of bandit algorithm with another function that's generating essentially prior values. So these are the Q numbers in your MCTS nodes. So there are a few different ways of actually using deep convolutional neural networks, but essentially what they're doing is providing some sort of prior value for the various actions at each state or at each node in your MCTS tree. And the typical bandit algorithm that you're using is this one called UCB1 and or variations thereof. So for example, in AlphaGo, I think they actually use something called a polynomial UCB. Right, so the determinism of UCB1 is, it can be a problem for parallelism. This is why people use virtual losses when they're doing parallel or asynchronous MCTS. However, we actually have a slightly simplified case, which is we're looking at a batch MCTS. So within a batch, we can replace a deterministic bandit with a stochastic one. So essentially what we're doing is, rather than deterministically sampling what is the best node to traverse in the tree, we can do a random sample. So this achieves a very similar effect. And what we do is we're actually replacing UCB1 with something called Thompson sampling. Thompson sampling is actually a pretty old algorithm. I think it dates back to the 1930s. But it has pretty good empirical theoretical properties, and it's become quite popular in the past few years. So just to summarize, we're using Thompson sampling of the tree policy to come up with a random sample of tree traversals. And then from those random tree traversals, we're performing a batch of rollouts simultaneously using convolutional rollout policy. All right. So how well does this actually do? So we took a recent version of Apache and we actually implemented a batch MCTS. This version is using a deep convolutional neural network in both the tree policy and the rollout policy. So in the tree policy, it's using a relatively deep one, similar to the one from the Dark Forest paper, although the accuracy of ours is, I think, slightly less. We spent some less time actually training it. So we can get roughly 92% with 1,000 rollouts versus Apache with 2,000 rollouts. So compared to Dark Forest, this is kind of in the same range. I think the AlphaGo number here is using a slightly different criteria. They have, I think, a time limit instead of a rollout limit. Yeah, so this is, it's possible to achieve a similar performance to some of these other state-of-the-art programs. One other interesting question is, what happens when we actually vary the batch size? Presumably, if your batch size is, let's say, the same as the total number of rollouts you're doing, then you're not really doing MCTS anymore. You're just doing straight up Monte Carlo tree, not tree search, but just Monte Carlo sampling. So at the very lowest limit of batch size of 1, that's essentially sequential MCTS, and somewhere in between, you might see a sort of trade-off between your batch size, which gives you better performance, and the number of batches, which is essentially, you want more of those in order to simulate the actual tree search itself. But what actually happens is that the win rate it seems pretty constant within a relatively large range of your batch size. So up to around a batch size of 64, which is a pretty comfortable number for actually running on a GPU. You can see that the win rate is kind of hovering around 90-ish%. After you go up to around 128, so I think the total the total number of rollouts here, I think, is 1,024. So a batch size of 128 corresponds to simply a total of 8 actual updates of your MCTS tree. 8 is pretty small, but somehow then it's still able to get 84%, but it drops off pretty quickly after that. So this is kind of encouraging. It means that for pretty standard numbers of the batch size, which run well on the GPU, small powers of 2 essentially. This you can see a pretty the win rate, the performance is pretty constant. Okay, so actually doing this in practice. All right, so I wrote a program called Holmes. So we this was competing at the 9th UBC Cup earlier this year in March in Japan. So that was an interesting and fun experience. But I guess some of the lessons were that, well, the actual throughput of your convolutional networks compared to, let's say, patterns it still leaves something to be desired. So I can get something like 250 raws per second per GPU. I think this was on like a Titan X. So that's not bad, except that actual pattern lookup policies can achieve something like an order of magnitude more. And the 3,000 to 5,000 raws per second isn't really a rigorous number, but that seems to be a nice ballpark range for typical MCTS programs. One of the things here is that if you look at CPU performance, that's been relatively constant for the past, I guess, over the past many years, maybe a decade or so. But GPUs have been improving quite a bit, simply because of increases in parallelism. So if you're paying attention in the news, there's this new Tesla P100 chip, that seems to give us, in terms of peak flop performance, maybe 3x. So we can go from, let's say, 250 to 750 just by spending some cash and buying some new hardware. So there's some more improvements in hardware that's possible, and maybe the number of raws per GPU number can actually increase in the future and match the per CPU. But that's kind of that's kind of in the future. I guess for now, if you're trying to get maximum throughput on simple rollout policies, you're probably actually better off with pattern-based ones. On the other hand, if you actually, in theory, it's actually possible to do some interesting research. You can probably get some mileage out of using the batch convolution instead. So that's that. Any questions? Yes.
In your batch selection, do you need to ensure that you end up with a set of unique leaps?
Yes, that's basically the purpose of the Thompson sampling. So essentially you end up with a set of unique traversals, and unique traversals have unique leaps. Yes.
How have you used the treat policy with Thompson sampling?
Okay, so I guess there are several ways to do it. The way I do it is, okay, all right. So MCTS normally has these Q values. So the version of Thompson sampling I'm doing is, I guess you would call it binomial Thompson sampling. So given the Q values, you essentially have a win rate at each node, and then from the win rate you can define a beta distribution. It's basically kind of the dual of the binomial distribution. And then what Thompson sampling is doing is you're sampling from each of those win rates for all the actions, and then selecting an action based on that. So the way I'm actually using the convolutional net there is I'm basically using it as a prior. I'm initializing the Q values with like constants essentially based on what the convolutional net is saying. So.
More questions or comments? I have one question.
Yes.
Are you part of the Homes team?
Yes.
Yes. And did you think about let your bot play on KGS?
This was actually, so I would have liked to do that. All of this was basically done on lab hardware, so I couldn't really spare a whole lot of cycles on actually playing.
You know, there are these monthly tournaments.
Oh yes.
And it would really be nice to have some more bots in there.
Yeah.
In particular, also yours, so you are cordially invited.
Yeah, definitely. Yeah, it's mostly just balancing a time of this versus doing other research. Yeah, I guess there is actually a whole lot of code that I've written for this, which I could also open source. Although I guess Dark Forest also open source theirs, so I mean people could look at that too. So yeah.
Okay. So, thanks again for the nice presentation.